Ideal and non-ideal solutions. Liquid-liquid solution can be classified into ideal and non-ideal solution on the basis of Raoult's law. First one, ideal solutions. The solutions which obey Raoult's law over the entire range of concentration are known as ideal solutions. Uh, Two more important properties are there for ideal solution, which are delta H mixing. That means enthalpy of mixing of pure component to form solution is 0. That means no heat exchange is taking place during solution formation. If we are mixing a solvent and solute to form a solution, no, there should not be any heat exchange. Then the solution will be ideal. Next one is delta V mixing is equal to 0. That means volume of mixing is also 0. That is, no change in volume take place when we mix a solvent with a solute to form solution. That means if you have 10 ml of solvent and 10 ml of solute, and if you mixing together, if you are getting 20 ml of solution, that means delta V is equal to 0. That type of solution are called the ideal solution. We can explain this with the molecular level also. If we are let us consider A as solvent and B as solute. Okay, and in pure solvent, AA interactions only will be present. AA interaction means intermolecular attraction between A and A will be present in pure solvent. Only will present in the solvent, pure solvent. And in pure solute, BB, intermolecular attraction between B and B will be present in the pure solute. Okay, when it joined together to form solution, in addition to AA interaction and BB interaction, AB interactions also will be present. And if the intermolecular attractive force between AA and BB are nearly equal to those of between AB, this leads to ideal solution formation. Whenever AA and BB interactions are nearly equal to AB interactions, then we can say it as the solution is ideal. And perfect ideal solution is rare, but some solutions are nearly ideal in behavior. For example, normal hexane and normal heptane is an ideal, a nearly ideal solution. Another one, bromoethane and chloroethane. And the third one, benzene and toluene are nearly ideal solutions. Non-ideal solution. The solution which does not obey Raoult's law over the entire range of concentration are called a non-ideal solution. Ideal solution obeys Raoult's law, no? That means Pi is equal to Pi0 into Xi. Which does not obey means Pi is not equal to Pi0 into Xi. That means the vapor pressure Pi should be may be higher or lower than the expected one. If the vapor pressure is higher than the expected Raoult's law, we can say it as positive deviation, and if it is lower than the expected one, we can say it as negative deviation. Okay, we can plot a graph between vapor pressure and the mole fraction. We have already drawn that line with the equation. I will show you that. With the equation P total is equal to P10 plus P20 minus P10 into X2. And we have already plotted a graph like this. Okay, this graph. Using these three equations, we have plotted this graph for ideal solution only. That means which obeys Raoult's law. And what will happen if they are not obeying Raoult's law? Okay, so this dotted line represent the ideal solution. Okay, and this one is P1 plus P2 graph. And here this if we are plotting a line, let me take a pencil. Okay, if we are plotting a line, no, with here you can see that. Okay, and for at this position, at when x is equal to this one, this place, you are getting vapor pressure here, not here. This is the expected one. That is the solution follows Raoult's law, get this vapor pressure. Okay, from here only. But the expected one, I mean here for the solution exhibiting positive deviation having a value of vapor pressure here. So higher vapor pressure is there. Okay, so that we can say that positive deviation taking place here. For other graphs also, P1 and P2 also having higher vapor pressure that expected. Okay, and for negative deviation graph, no, here this is the graph showing solutions obeys Raoult's law, and here the vapor pressure is lesser than the Raoult's law vapor pressure, no, so we can say it as negative deviation graph. Okay, and the same as in P1 and P2 also, there is decrease in vapor pressure as expected. Okay, so we can say that negative deviation taking place. Example 4, solution showing positive deviations. First one, ethanol and acetone. Second one, carbon disulfide and acetone. In the case of positive deviation from Raoult's law, AB interactions are weaker than those between AA and BB interactions. That is in the case of intermolecular attractive force between solute solvent AB interactions are weaker than those between solute-solute and solvent-solvent molecule, that is AA and BB molecules. This means that in such solutions, molecules of A or molecules of B find easier to escape than in pure state. This will increases vapor pressure, and finally it shows positive deviation from the Raoult's law. Okay, if you are taking the case of ethanol and acetone, if you are taking ethanol in the pure form, that is ethanol as such, they should have a hydrogen bonding between ethanol molecule like this way. This is ethanol, this is another ethanol. So here electronegative oxygen is present here, and electropositive hydrogen, so that it can easily make hydrogen bonding between. Okay, and hydrogen bonding, due to this hydrogen bonding, the vaporization decreases, no? So the pressure also lower. When we add acetone, the acetone molecule will comes in between two ethanol molecule, so that it breaks the hydrogen bonding. As a result, the vaporization increases. Vaporization of ethanol molecule increases, and thereby vapor pressure also increases, and show positive deviation here. Same in the same way we can explain carbon disulfide and acetone molecule solutions also. That is, the interaction dipolar interactions between solute solvent molecules are weaker than the dipolar interactions between solute and solvent molecules. So here also showing positive deviation. An example for solution showing negative deviation: phenol and aniline. Next one, chloroform and acetone. In the case of negative deviation, the intermolecular attractive force between AA and BB are weaker than those between AB, so that decrease in vapor pressure will be there, that resulting in negative deviation. Here in the case of phenol and aniline, no. If you are taking phenol, they have an intermolecular hydrogen bonding between phenol and phenol like this way. And in the case of aniline also, they have a intermolecular hydrogen bonding between aniline molecule. Okay, nitrogen, lone pair of nitrogen forms hydrogen bonding with the hydrogen in the next aniline. And if you are taking the solution, when we mix phenol and aniline together, there also hydrogen bonding is there. Hydrogen from the phenol bonded with lone pair of nitrogen, okay, forming hydrogen bond. The thing is that the hydrogen bonding in the solution, that is phenol and aniline, no, that is stronger than the intermolecular hydrogen bonding in between phenol-phenol and aniline-aniline. So that the vaporization is less in solution than in individual state. So vapor pressure decreases so that negative deviation will be showing. And then next one, chloroform and acetone. In chloroform acetone, no, when when it combines together, chloroform and acetone, they're having an intermolecular hydrogen bonding. And so the vaporization is lesser and showing negative deviation. That means vapor pressure will be lower and showing negative deviation. So we can discuss some questions related to the topic. First one, what type of intermolecular attraction exists among the pair of methanol and acetone forming a solution? That is dipole-dipole interaction. Next one, if we are taking 10 ml of a liquid A was mixed with the 10 ml of liquid B. The volume of the resulting solution was found to be 18.9 ml. What do you conclude? Here 10 ml of A and 10 ml of B mixing. If you are getting 10 plus 10 20, then we can say it is an ideal solution. But here you are getting a resultant solution having a volume of 18.9 ml. That is volume is less than 20 ml. So decrease in volume taking place. So negative deviation. Delta V is negative. So that solution showing negative deviation from the Raoult's law. Acetone, third one, acetone and chloroform are mixed together with the reduction in volume. Volume get reduced. That means negative deviation. No. What type of deviation will be observed on the basis of Raoult's law? Negative deviation itself. Due to formation of intermolecular hydrogen bonding, the molecules of two constituents come closer to each other and hence reduction in volume take place. That is delta V solution is negative. So negative deviation is showing. Fourth one, A and B are liquids which on mixing produces a warm solution. Which type of deviation from Raoult's law is there? You are getting A, B mixing together to get, at that time you are getting a warm solution, no? Warm means exothermic reaction taking place. So delta H should be negative for exothermic reaction, no? That's why the solution show negative deviation because delta H value is negative. Next one, when two liquids are mixed, the resulting solution is found to be cooler. What do you conclude about the deviation from the ideal behavior? Just opposite. If you are getting cooler solution, no, that means endothermic reaction. That is delta H is positive, so positive deviation from ideal behavior. What type of liquid pairs show positive deviation, negative deviation from Raoult's law? We just studied only, no? Molecules for which AB liquid pair interactions are weaker than AA and BB interactions show positive deviation. When it is stronger than AA and BB interactions show negative deviation.